Hi everyone. Today I would like to go over an untraditional method that can be used to convert decimals to fractions, even decimals that have an incomplete period, such as this one. Allow me to explain. There are various kinds of decimals that different fractions can make. First, we have the terminating decimals. These are the most straightforward and are fairly easy to convert to fractional form. Next, we have the pure recurring decimals. These decimal expansions have a pattern that starts right after the decimal place. The pattern continues for a certain length and then repeats itself indefinitely. That repeating pattern is called the period. The bar on top specifies all the digits of the repeating period. Next, we have the mixed recurring decimals. These are similar to the pure recurring decimals in that they have a repeating period, but they also have at least one digit after the decimal point that is non-repeating, which is then followed by the repeating part. In these examples, the pure recurring decimal has a period of 6, while the mixed recurring decimal has a period of 1, which repeat over and over as shown here. If we have the complete period, there are some traditional methods to find the original fraction. We're going to go through them really quickly just to show that they work, but we're not going to go into detail about how to execute these conversions. There are plenty of resources on the internet about how to do this kind of thing. But as you can see, we were able to convert all of the decimals to their original fractions. But let me reiterate, this only works when we have the full period of the decimal expansion. Without that, these methods would not work. So here we have a pure recurring decimal that has a period of 28. You could theoretically convert this to fractional form using the method I just showed. But that requires finding the common factors of two 28-digit numbers, which is not an easy task. To make it even more challenging, what happens when you only have 10 of those digits to work with? This is what I'm talking about when I say a decimal has an incomplete period. How would you tackle this problem? You can pause the video if you want to think about it for a minute. The fraction we're looking for is some numerator divided by some denominator. Let's make a rectangle whose side lengths are proportional to that numerator and denominator. All we can do for now is make the numerator equal to the decimal expansion and the denominator equal to 1. Now we're going to see how many squares of side length 0.379 can fit into that rectangle. To find this, we can divide 1 by the decimal, and we get 2 with roughly 0.63 left over. If we now redefine the square to have a side length of 1, then the rectangle's length can be redefined as 2.63. We'll split off the whole number part from the part after the decimal place. We're now able to define the leftover gray rectangle. Now let's see how many squares of side length 0.63 can fit into that rectangle. We'll again divide 1 by the decimal, which gives us 1.57. Like before, we can redefine the side length of this orange square to be 1, making the height of the combined orange and gray rectangle to be 1.57. We'll split off the whole number from the decimal again so we can define the gray rectangle. Continuing our pattern, we'll divide 1 by the decimal to see how many squares can fit into the gray rectangle, and we get almost exactly 1.75. Because we started with a limited number of digits, some error has crept in and given us that 19 at the end. We're probably safe in assuming that the answer should be exactly 1.75, so we'll cut off the error and keep going. Making the side length of the green square equal to 1, the combined green and gray rectangle has a length of 1.75. Splitting off the decimal part again, we get a rectangle of dimensions 0.75 by 1. Dividing 1 by 0.75 shows us that 1 square plus 0.33 left over fits in the rectangle. As always, we'll redefine the side length of the purple square to be 1, making the height of the combined purple and gray rectangle to be 1.33. This makes the dimensions of the new gray rectangle 1 by 0.33. And finally, we'll divide 1 by 0.33 and see that exactly 3 squares fit into that rectangle. Like before, we'll discard the rounding error. It cropped up again because I'm only keeping 10 digits of accuracy at each step, just to show that even fairly basic calculators can do these calculations. The red squares are now redefined as having a side length of 1. We can now redefine the other squares in terms of the smallest squares. And there you go. We were able to find the original fraction using this method. What probably wasn't obvious was that we were using the math of continued fractions along the way. We're going to go through the same process again, but we'll also build a continued fraction at the same time to help show us the math behind it all. We'll start with the same decimal as before. We'll again define a rectangle using the decimal as the numerator and 1 as the denominator. We'll see how many squares of side length 0.379 can fit into the rectangle by dividing 1 by the decimal. Doing some algebra, we can make 1 over 2.63 equal to the original definition of the rectangle. We can now redefine the rectangle in terms of the new fraction, making the height 1 and the length 2.63. Following the same steps as before, we'll split off the whole number part from the part after the decimal place. Like before, 1 square fits into the new gray rectangle. Doing some algebra, we see that 1 over 1.57 equals the original definition of the combined orange and gray rectangle, allowing us to redefine it in those terms. We continue following this pattern all the way down. We can now see what the filled rectangle is expressing in mathematical form. This is the continued fraction form of the fraction we are looking for. As we collapse the rectangle again, we'll do the same to the continued fraction, showing their equivalence. 1 plus 1/3 is 4/3. 1 divided by 4/3 is 3/4. 1 plus 3/4 is 7/4. 1 divided by 7/4 is 4/7. 1 plus 4/7 is 11/7. 1 divided by 11/7 is 7/11. 2 plus 7/11 is 29/11. And finally, 1 divided by 29/11 is 11/29, which is the fraction we started with. Using continued fractions, you can actually find original fractions that are quite large using this method. We'll take this rather big fraction as an example. If we expand it into its decimal form, the digits don't start to repeat for quite a long time. In fact, the period of this fraction is over 50,000 digits long. Needless to say, it would probably ruin your day if you tried to convert this to fractional form using traditional methods. We'll go through the process fairly quickly just to show that it can be done relatively simply. And there you go. Continued fractions can help us convert fractions of even this magnitude. But there's something we haven't talked about yet. Irrational numbers. These are numbers like pi, e, phi, or the golden ratio, and the square root of 2. The thing about irrational numbers is that their digits follow no particular pattern at all, and they cannot be expressed as a ratio. In other words, we can't convert these to fractional form because it's not possible. But what we can do is make good fractional approximations of these numbers. Let's take pi as an example. We'll begin converting it to continued fraction form. Because pi can't be expressed as a ratio, this continued fraction will go on forever. The 3 dots signify that this continued fraction actually keeps going. To save some space, we're going to represent this continued fraction in linear form. We just need to take the leading term under each division since we know they are all divided by 1 all the way down. The linear form is expressed like this, which saves us a lot of space. Now we want to use these terms to make fractional approximations of pi. If we take the first 2 terms and convert that back to the expanded form of the continued fraction, we can then simplify that to a simple fraction. That gives us 22 over 7, which as you can see is already a decent approximation for pi. Let's take the first 3 terms now and see what it gives. And let's keep going down the line a couple more times to see how accurate we can get. As you can see, we were able to get really great approximations for pi without using too many terms in the continued fraction. These fractions are called the convergence of the continued fraction. It's actually been proven that the continued fraction convergence of any irrational number are the best fractional approximations of that irrational number for their size. The 355 over 113 approximation is especially impressive for its size, coming in at over 99.99999% accurate, with only a 3-digit denominator. Next, we'll see that applying this process to the golden ratio produces unusual results. Let's start by separating the 1 from the rest of the decimal. We'll do our usual process of dividing 1 by the remainder and taking the inverse of that to replace the original decimal. But something strange happens here. The golden ratio just showed up again. That means if we continue the process of making the continued fraction, we'll just keep making 1s as the leading term. Every term in the continued fraction of the golden ratio is 1 going to infinity. We'll represent this in linear form like we did with pi. Now let's see what happens when we find the convergence of this continued fraction. The first 2 terms give 2, which honestly isn't that great of an approximation. The first 3 terms give 1.5, also not great. And as we keep going, we see that none of these convergents are doing that great of a job for their size. Let's actually take the convergence of the golden ratio and graph them according to their percent error on the y-axis and the denominator size on the x-axis. Note that both axes are log scaled. For comparison, we'll plot the convergence of pi as well. Let's also put e and the square root of 5. We'll also add a bunch of other square roots for good measure. As we can see, the fractional approximations for the golden ratio are all really quite bad for their size, with no exceptions. They perform consistently worse than the fractional approximations for other irrational numbers, with only the occasional data point passing the blue golden ratio line, but never consistently so. It's because of these consistently bad fractional approximations for the golden ratio that has earned it the title of the most irrational number. In other words, it is the irrational number that is hardest to find a good fractional approximation for. We also see this red data point on the graph that stands well below the general trend. This is 355 over 113, which is the excellent approximation for pi that we talked about earlier. This approximation is so good that it's performing as well as fractions way up here that have denominators 10 times its size. Lastly, here we have a decimal expansion that came from a square root of some number. We can even use continued fractions to find that original square root. Let's begin converting it to continued fraction form. This particular continued fraction actually keeps producing 6s indefinitely. When this kind of thing happens, then you can know with certainty that a square root was used at some point to make that decimal. We'll make x the simplified answer we're looking for. We'll put parentheses around this part of the continued fraction so we can notice something important. We'll also move the 3 to the other side. What's interesting is that the part inside the parentheses is actually equal to the whole right side of the equation, since the continued fraction keeps going forever. The part in parentheses excludes the first 1 over 6, but that doesn't matter since it still goes on forever. So since the right-hand side of the equation equals x minus 3, that means that the part in parentheses also equals x minus 3. So we can actually replace that with x minus 3. Now it's just a matter of doing some algebra and solving for x. Solving for x gives the square root of 10, which we can verify does equal the decimal we started with. If you enjoyed this video, please leave a like, and subscribe to the channel to keep up with more content.